Hello. Today we're going to be looking at lesson 2.8, which is looking for a pattern in integer exponents. So I want to start just by looking at what happens in the top scenarios. We have two similar problems, but reversed in a way. So first we have 2 to the 7th power over 2 to the 5th power. And when we take a look at that, we know that when we're dividing two powers with the same base, we can subtract the exponents. So if we were going to write this out, for example, expand it, we could just simply write it out as 2 7 times in the numerator. Squeeze it in here. Over 2 5 times in the denominator. And anytime you're dividing one of the 2's by itself, it's going to cancel and give you 1. So when we cancel out one of them, 2, 3, 4, and 5 of them, leaving us with just 2 squared or 4. That's, of course, illustrating the property of the division, where if we subtract the exponents, we would have done from the very get-go 2 to the 7 minus 5, and we would have got 2 to the 2nd, which does equal 4. But now let's take a look at this one over here, where we have 2 to the 5th over 2 to the 7th. So if you think about it, if we have 2 to the 5th, that now means that we have the 5 2's in the numerator, and we have 7 2's, sorry about that, in the denominator. And so when you go to cross them out to simplify them, the 5 of them will cancel, and you'll be left with 1 in the numerator over 2 times 2, or 2 to the 2nd power, in the denominator, giving us a final answer of 1 to the 4th. So very interesting. Different from what we've seen in the past. So I now want you to look at this quick table. You can see first, in the first column here, we have everything written in exponential form, and then this is the expanded version, and then if we were to evaluate it, we'll see what it actually equals. So if you have 3 to the 3rd power, 3 times 3 is 9, times 3 again would be 27 evaluated. 3 squared is just going to be 9. 3 to the 1st is just 3. Anything to the 0 power, we remember, is equal to 1. And then when we get something to the negative 1st power, what actually happens is it's going to equal 1 over 3 to the 1st. So just like we saw up here with 2 to the 5th over 2 to the 7th, if we would have subtracted those exponents, like we did over here using the division property of exponents, because we have two powers with the same base, we could subtract 5 minus 7. And what we would actually get is a negative exponent. And what that tells us is that negative exponent actually becomes a fraction, where 1 is our numerator, and the exponent now is positive, and when we evaluate it in the denominator, we get 1/4. So if we have 3 to the negative 2nd power, that's actually going to equal 1 over 3 squared, or 1 over 3 times 3, which is 1/9. So when you have a negative exponent, it doesn't become negative, which is a common misconception. It actually becomes a fraction. So I'm just going to make a quick note of that, but you will see that every time. So let's go ahead and try a few others quickly. So if we take a look at this one, 7 squared, we know that's just 7 times 7, which is 49. But 7 to the negative 2nd power is actually 1 over 7 squared, because the whole power moves to the denominator, the exponent becomes positive, and then you can evaluate it to get 1/49. If we were going to expand and evaluate, or even just use the division property of exponents in this one, we would have 3 to the 4 minus 6 power, which is 3 to the negative 2nd. We never leave a negative exponent in our final answer, by the way. So when we see that, we can't circle it and call it a day. We actually have to turn this into a fraction. Again, moves into the denominator, our exponent becomes positive, and then when we evaluate that, we would get 1/9. On the next page, let's take a look here. We have 10 to the negative 4th. So if you think about that, that's going to be, if written as a fraction, it would be 1 over 10 to the fourth. And 10 to the fourth power is 10 times 10, which is 100, times 10 again, which is 1,000, times 10 again, which is 10,000. So this is 1/10,000th, 1 followed by 4 zeros. And because it also asks us for decimal form, if you just say it and think about it, 1/10,000th means that there would be a 1 in the 10,000ths place. So behind the decimal, we know that the first is the tenths, hundredths, thousandths, and then 10,000ths. So that is the other way that we could express that answer. For 2 to the negative second power, we would write 1 over 2 squared, which is 1/4. Down below, it says write with positive exponents. So we're going to rewrite this. So we have -4 to the negative third power. Notice this is the first time we've seen a negative base and a negative exponent. So if we were going to write that out, it would become 1 over -4 to the positive third power, because we have a negative base and an odd exponent. If we were to evaluate that all the way, which we could do quickly here, we would actually end up with a negative, because we have the odd exponent. So we would end up with -64. So it would be -1/64. Now over here, because we're multiplying two powers with the same base, 10 squared times 10 to the negative second, we could actually add the exponents first. So if we did that, we would have 10 to the 0 power, and anything to the 0 power actually just equals 1. Next, we have 4 squared divided by 4 cubed. So that's really going to be 4 to the second minus 3, which is 4 to the negative first. We can't leave that negative exponent, so we would rewrite it as 1 over 4 to the first, or 1 to the fourth, 1/4, I'm sorry. The next one, we have a variable as the base, but still the same process. G to the negative fourth would become 1 over g to the positive fourth. Now there's nothing to evaluate here because we have a variable. Then in the next one, 5 to the negative second over 5 to the negative fifth. So again, subtract your exponents, so -2 minus -5. But think about that for a second. If you're subtracting a negative, you're really adding a positive. And so -2 plus +5, this one actually won't be a negative exponent. It would just be 5 to the third power, or 125. We have 3 terms in the next one. 3 squared times 3 to the negative third times 3 to the fourth. I shouldn't have said terms, but we have 3 components here. So we could add all of these exponents because they all have the same base. So it'd be 2 plus -3 plus 4, which would give us 3. We have 2 plus -3 is -1, plus 4 is 3. So it'd be 3 to the third power, which is 27. -5 to the negative second power. Notice the entire -5 is part of the base because it's in parentheses. So when we evaluate this, it would become 1 over -5 squared. And so 1 over 25 would be our final answer. In this next one, in the numerator, we would evaluate within the parentheses first. So 5 minus 3 is 2. So we have 2 to the fourth power. In the denominator, we have 1 minus -1, all in parentheses, but those two negatives both become plus, so that also is 2, this time to the third power. So we have 2 to the fourth divided by 2 to the third, which is actually just 2 to the first, or 2. In this next one, we have y to the fifth times y to the -6 times y to the seventh. So they all have the same base. So we're going to add up the exponents, 5 plus -6 plus 7, and we will end up getting y to the 6th power. And that's our final answer. And then lastly, because we have a negative exponent in this last one, we can't leave that in our final answer, so we will rewrite this as 1 over x to the positive third power. But that's as far as we can go. All right, thank you.